In the fundamentals chapter, we talked about intermolecular interactions. During a phase transition, a substance preserves its integrity, so there are no changes in the number or the strength of its covalent bonds. However, with a change in phase come changes in the relative orientations and distance between molecules. Phase changes are therefore accompanied by changes in intermolecular interactions. The temperature at which a phase change occurs at a given pressure and the heat associated with the change in these intermolecular interactions are characteristic properties of a substance that relate to the strength of these intermolecular interactions. Phase transitions are typically observed under constant pressure, so the heat associated with such a process is equal to the enthalpy change. Enthalpy changes for phase transitions are typically reported for 1 mole of substance at the standard pressure of 1 bar and at the standard transition temperature, that is, at the temperature where the phase transition occurs at 1 bar. Standard enthalpies of phase transitions and standard transition temperatures are given for some common substances in the following table. Freezing points could have been called crystallization points and have the same value, of course, as melting points. Boiling points could also have been called vaporization temperatures. In general, as the strength of intermolecular interactions increases, so do the melting point, boiling point, standard enthalpies of fusion, and vaporization. Recall from the fundamentals chapter that intermolecular interactions are strongest in the solid state and for the most part absent in the vapor state. Intermolecular interactions would be totally absent if the vapor behaves like an ideal gas. All standard enthalpies of fusion and all standard enthalpies of vaporization are positive. This is so because one needs to supply heat to a crystal to break some of its intermolecular bonds to make a liquid. Similarly, you need to supply heat to a liquid to break the vast majority of the remaining intermolecular bonds to form the vapor. The differences in intermolecular interactions among the solid, liquid, and vapor phases explains why enthalpies of vaporization are always much greater than enthalpies of fusion. Finally, note that the standard enthalpy change for a phase transition depends on the temperature. For instance, in the case of water, the heat of vaporization increases by 10% or so when the temperature at which the phase change takes place decreases from 100 degrees Celsius to 0 degrees Celsius. We will see throughout this course that there are a lot of parallels between phase changes and chemical reactions. Both types of processes occur at constant temperature and constant pressure. Both are processes for which initial and final states have different energy levels. For chemical reactions, the change in energy arises from the redistribution of covalent bonds between the atoms involved in a reaction. In contrast, in phase transitions, the change in energy arises from the change in intermolecular interactions from one phase to another. So, we will write phase transition symbolically in the same way that we would write chemical reactions. Specifically, we will use thermochemical reaction equations to describe the phase transition process and inform the reader about the energetics of the process. For the fusion or melting of crystalline ice, that is solid water, we would write 1 mole of H2O solid gives 1 mole of H2O liquid. And on the same line, delta fusion H standard for H2O solid equals 6.01 kilojoules per mole. Note that the delta H is given in the standard conditions at P standard equal to 1 bar for 1 mole of reaction equations. That is here for 1 mole of pure water. The sign of delta H relates to the direction of the arrow, that is, in this case, positive delta H for the fusion or melting process. If we were interested in a change in enthalpy at 1 bar for 2 moles of H2O solid, we would write the following thermochemical equations. 2H2O solid gives 2H2O liquid, and of course delta H for this process would be equal to twice the standard fusion enthalpy change, that is 12.02 kilojoules, no longer per moles. If we were interested in a crystallization process, we would write the following thermochemical reaction equation. 1 mole of H2O liquid gives 1 mole of H2O solid with delta crystallization H standard equals minus delta fusion H standard equals minus 6.01 kilojoules per mole. As already mentioned in the previous slide, the enthalpy changes for fusion, vaporization, and sublimation are all positive. This is so because for transition from the solid to the liquid, or from the liquid to the vapor, or from the solid to the vapor, there are stronger intermolecular interactions in the initial state, that is, the molar enthalpy is more negative, than in the final state, and heat must be supplied to the system to decrease these interactions. Conversely, enthalpy changes for crystallization, condensation, and vapor depositions are always negative. Finally, note that for a given substance, the enthalpy of fusion has a magnitude much lower than the enthalpy of vaporization, which is itself smaller than the enthalpy of sublimation. Finally, remember that the magnitude of delta H vaporization standard measures the strength of intermolecular interactions greater in 1 mole of water than in 1 mole of methane, and that the standard transition enthalpy changes depend on temperature. I am sure you must be wondering why no mention was made of standard enthalpies of sublimation on the previous slides. Are these values not known? They can actually be easily calculated if we remember that enthalpy is a state function. Indeed, we know that the change in enthalpy of a system as a result of a process between two states is independent of the path chosen between these states. Sublimation is the process that transforms a crystalline solid phase to the vapor phase. Let us assume that we are interested in the standard sublimation enthalpy near the triple point, that is at 273.16 Kelvin and 0.007 atmosphere. To transform the crystalline state to the vapor phase, we can take the alternate path that goes to the liquid state. From the standpoint of thermodynamics, the changes in enthalpy are the same for both paths, as long as we start at the same place for both paths, here in the crystalline solid state, near the triple point, and end up at the same place for both paths, here in the vapor phase near the triple point. We know that the standard enthalpy of fusion, which is 6.01 kilojoules per mole, and the standard enthalpy of vaporization, which is 45.07 kilojoules per mole. So the enthalpy of sublimation is the sum of the enthalpy of fusion and the enthalpy of vaporization. That is, delta sublimation H standard is equal to 51.08 kilojoules per mole.